Section 6.1, exploring the graphs of polynomial functions. So first of all, let's look at the definition of a polynomial. Polynomial function. Poly means many, nomial means number. So many numbers. Function means x depends on y. Something depends on something else. F of x is the same as y, so y depends on whatever we put in for x. It's a polynomial function in one variable is a function that contains only the operations of multiplication and addition with real number coefficients. So it's 6, 3, -4, 9. Those are real numbers. Whole number exponents, cubed, squared. This is 1. And 2 variables. The degree of the function is the greatest exponent of the function. So we have in the polynomial function f of x equals 6x cubed plus 3x squared minus 4x plus 9. Here's our biggest or greatest exponent, so the degree is 3. The degree determines the shape. And that's what we're going to go through today. We're going to look through the shape. And so Naomi goes through and she wants to see, they're appreciated for the simplicity. What else do we want to know? We remembered that there's characteristics, okay? So the first type of polynomial function we're going to look at is a constant. We're actually going to do one before Naomi here, okay? And whenever I have to graph, what I do is I use Desmos graphing calculator. You could also use a graphing calculator like a handheld one, but I just Google Desmos graphing or Desmos graphing calculator, and there's a really good calculator that comes up. So a constant function means y, or f of x, I like to put y because it's simpler, is equal to 4, okay? And it's just a line. Or we could go y is equal to -3. It's a constant function. There is no values of x, so no matter what value of x we put in, the function remains constant. Okay? The next polynomial function we're going to look at is degree 1. This is called a linear function. You guys have done a lot of work with linear grade 9 and up. So here's the function x plus 1. If you look at the graph, and the graph's already shown here, you can see that it has one x-intercept right here. It has one y-intercept. It's end behavior. This is important. The description of the shape of the graph from left to right. So it goes from quadrant 3 to quadrant 1. If you forget your quadrants, they're right here. The domain, this graph goes on forever and ever and ever, and that can kind of be shown pretty good here. So let's do x plus 4. That's another linear one. No matter how much I zoom out, that red line goes on forever and ever and ever and ever. Doesn't matter how much I zoom out. Okay, I'm going to zoom back to a reasonable amount now. There we go. Okay, so it's x and y values go on forever. Its domain is all real numbers, so it goes on every number possible, not just whole numbers, anything in between, and same with its y. Here's another linear function. This looks a little different, but it's still linear, it's still degree 1 because x is only raised to the power of 1. Okay, so the next thing we're going to look at is quadratic. So quadratic means that the biggest degree is 2. And if you don't know how to write that on the Desmos graphing calculator, you just use the little hat, and that brings it, the hat is above the 6. So now we have x squared, and we could have x squared plus 3x plus 4. We could also have x or 3x squared minus 7x x plus 2. Okay, so these are both quadratics. They're both raised to the power of 2. And now we're going to look at what that means in terms of, we should do a -1 too. I just thought of this. Negative x squared plus 5x plus 3. Okay, so here we have a bunch of graphs. I'm going to just zoom out a bit so we can see them. So these are all quadratics, and we're trying to look at how these behave. Okay, so let's look at the different categories we're looking at here. So we want to know the number of x-intercepts and number of y-intercepts. So looking here, we see that it really depends. This orange one has 2 x-intercepts, 1 y. This blue one has 1 y, 2 x. But this red one has no x-intercepts. So it can either have, and we could actually make it, if we changed this one to just, oops, not that. There could also be a way where we could take this graph and it could be right, if we could extend this, if I could, it could touch just once. So its x-intercepts could either be 0, 1, or 2. It's always going to have 1 y-intercept. Next, it looks at end behavior. Well, it depends on the leading coefficient. So this has a positive 1. This one originally had a positive 3, and this one had a negative. So if it's a positive leading, it starts in quadrant 2 and ends in quadrant 1. But if it's negative, it starts in quadrant 3 and ends in quadrant 4. So it depends. In terms of domain and range, no matter how much we zoom out, we have every single x value possible and every single y value possible. So we say x is a member of the reals and y is a member of the reals. Okay? And the other thing it talks about is turning points. So let's look at this red graph. All of the y values are decreasing, 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 and then all of a sudden it turns and the y values are increasing. Same here, decreasing, decreasing, increasing. The orange one is increasing, 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 decreasing. So there's that one point where the graph turns. Okay, next thing we're going to look at is a cubic. So now let's raise all of these things to the power of 3. To the power of 3. And let's add a squared term in. And we could add 4x plus 7. Okay. We got to raise that to the power of 3, to the power of 3. So here we have a couple of graphs. Let's get rid of this graph. And let's make this negative so we can see the difference between a negative and a positive. And let's make that a squared. Okay. So looks like we have a couple graphs there. 2x plus 2. Okay. So here we have a couple cubics. I don't like my red one as much as I like the blue one. Couple things we can see here. So it is a cubic. Its number of x-intercepts. This one has 1. This one has 3 x-intercepts. And we could also create a graph that had 2 x-intercepts. So it can either 1, 2, or 3. It's only going to cross the y once. Now it's end behavior. This blue one, which is negative, starts in quadrant 2 and extends to quadrant 4. This one, because it's positive, goes from 3 to 1. So depending on where, if it's positive or negative, is where it starts and ends. In terms of domain and range, if we zoom out, we could hit every single x and every single y. It's going to take a while for us to get all those y's, but if this extended on forever, you can tell it keeps on going out and it would hit those y's. Now, turning points. This blue one shows it really well. So we have decreasing y values, now increasing. So that's one turn, and now decreasing again. So that means it turns twice. There's twice that it turns. Let's look at this one. Increasing, 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 increasing. No turning points. This graph is always increasing. So a cubic, or something with a highest degree of 3, always has 0 or 2 turning points. Okay? So just to summarize what we did, there's a really good sheet, and this is also found in the last page 382 in your textbook. It summarizes all of this information. So graphs of polynomial functions have the same common characteristics. Simple sketches displays all the possibilities. So this is pretty valuable. So the questions you're going to do is going to look at these characteristics. What we're going to see is everything that has an odd or an even degree. So if we had x to the 4th, it might act like a quadric, and x to the 7th, because it's odd, are going to act like cubics. That's what we're going to see eventually.